Welcome to Information Technology Video Developer Network. My name is Abdurrashid Hamid. I'm a certified Microsoft specialist working for Cyber Bionic Systematics. The topic of our lesson today is machine mathematics and numeral systems. Everybody has heard of the term bit. Let's look at the real representation of a bit in this slide. As you can see, there is a diagram, a difficult diagram representing a bit. This diagram is a complex construction. It consists of resistors, transistors, and so on and so forth. We are not interested in this. I'm not going to use this diagram to represent a bit in this lesson because it will just confuse you. So what I will do is I will just tell you what a bit is, and I'll also give you some examples and we move on from there. A bit is the basic unit of information in computing and digital communications. A bit is sometimes called a flip-flop in electronics. And you can see a bit has two values or two states. What does this mean? This means that a bit can either represent 0 or it can represent 1. So just imagine that and keep it like this. A bit has two values. If you want more information on this complex diagram, you can check this website below. Now, let's move on to the meaning of these two values or two states, and I'll give you some more examples. When we are talking of two values, we can have a thumbs down or a thumbs up. These are two examples of what two values can mean. Let's imagine that 0, it's thumbs down, 1, it's thumbs up. In this case, we have a full glass of water representing 1 and an empty glass of water representing 0. So this also gives you an example, or should I say an idea of what a bit does. Now, I'm not going to use two glasses or two thumbs or a resistor or something like that. What I'm going to use is a bulb. Imagine that this is a bit. And throughout this lesson, I'll give you examples using light bulbs. I think it's easier than having a diagram of flip-flops or difficult diagrams containing resistors and transistors and so on and so forth. So let's lay the rules down. On this slide, you can see the states of a bit. If the bulb doesn't glow, it means it's not working, and we're not concerned with this. Let's just look at a partially glowing bulb and a fully glowing bulb. If I say that a partially glowing bulb should represent 0 and a fully glowing bulb should represent 1, I guess you'll understand the whole concept and you remember this. Okay, I know you're wondering what an apple and a pear are doing on our screen. Just give me a minute to explain and you'll understand everything. Now, in our previous slide, I told you that a bit can have two values. It can be 0 or 1, and we agreed that a partially glowing bulb represents 0 and a fully glowing bulb represents 1. Now let me just tell you something else. If, for example, we have two rooms, and in one room we have a light bulb, in the second room we have two switches. And you're sitting in the room where the light bulb is, and I'm sitting in the room where we have the two switches. And if I turn on the first switch, your bulb will glow partially. If I turn on the second switch, your bulb would glow fully. Now, if I turn on the first switch, the command or the instruction is you eat an apple. If I turn on the second switch, the instruction is you eat a pear. This is basically how instructions or commands are given to the computer. This is how a bit can change its state and give the computer different commands and different instructions. Now, this is the easiest case scenario where we have one bulb and two instructions or two commands. If I change it and I add one more bulb, we would have more commands and more instructions. Let me show you what I mean. Here you can see we have added one more bulb, meaning we have more commands or more numbers. Using two bulbs, we can give the computer 4 commands. You can see we have 0, 0, which means 0, instruction eat an apple. 1, 0, meaning 1, instruction eat a pear. And so on it goes. When you have 1, 1, in decimal it's 3, so you get to eat a pineapple. If you need to add more instructions, if you need more instructions or more numbers, then you have to add another bulb. If you have another bulb, you'll have double the command number and instruction number. Here we have added one more bulb to our scenario. In this case, we have 8 commands or 8 numbers. And the system or the principle remains the same. 0, 0, 0 means 0, eat an apple. 1, 0, 0 meaning 1, eat a pear. And this ellipses means that there are some more commands here, but we don't need to draw all the bulbs for you to understand. The last instruction here is 1, 1, 1, 7 to eat a strawberry. If you need more commands or instructions, what you need to do is you add another light bulb. If you add another light bulb, you will have 16 commands or 16 numbers. The principle still remains the same. You can go on and so forth until you have 16 commands. If you add another bulb, you have 5 bits representing 32 commands, and it remains the same. You keep on adding bulbs and we'll see what will happen. Adding one bulb, we have 64 commands. You can see that by just adding one bulb, you have doubled the number of commands you can have. If we add one more bulb to this scenario, we'll have 128 commands, exactly the double of 64 commands that we have on this 6-bit screen. Here we have 128 commands and the same principle. If your light bulbs glow all partially, all of their values are 0 and the result is 0 and you get to eat an apple. And you continue till you reach 127. Let's add one more bulb to our scenario and see. When we add one more bulb, it means now these bulbs represent 8 bits, since we agreed that each bulb represents 1 bit. Here you have 256 commands. The principle still remains the same. 8 bulbs, all having a value of 0, you get to eat an apple. And it continues till you reach all ones and a full value of 255, which is the maximum value that an 8-bit system can hold. On the next slide, I'll show you what a byte is. A byte is simply 8 bits put together. They are divided into 2, and you have one part here, the other part here. This part is called the junior tetrad. This part is called the senior tetrad. Now I want you to keep in mind that a byte can hold a maximum of 8 bits. If you need to add one more bit to this byte, you have to have another byte. Now you can have 9 bits but 2 bytes. A byte is a unit of keeping and processing digital information. And we go to the next slide, I'll show you more about a byte. Now let's take a look at the units of data measurement. The units of data measurements include kilobytes, megabytes, gigabytes, terabytes. We can also keep information in bytes and bits you remember. Now, 1 kilobyte is equal to 1024 bytes. 1 megabyte is equal to 1024 kilobytes. 1 gigabyte is equal to 1024 megabytes. 1 terabyte is equal to 1024 gigabytes. Everybody at one time or the other has seen something like this. This is a RAM and everybody knows it. It's just basically a combination of megabytes put together on a board. Let's take a look at what is inside of a RAM. In the inside of a RAM, you can have bytes, a lot of bytes. And you can see that we have bits, 8 bits per byte, and a lot of bytes inside each RAM. Let's take a look at how many bytes we have in 1 gigabyte of a RAM. If the size of your RAM is 1 gigabyte, then it is 1,073,741,824 bytes inside. Now you can see if you have 2 bytes or 4 bytes or 8 bytes, you can multiply this by the number of gigabytes you have in your computer. Let's take a look at how bytes are stored in a RAM. Bytes have what we call an address. This is basically the position of the byte in your RAM, starting from 0 to the maximum number of bytes you have. In this case, we have 1 gigabyte, meaning we have about 1,073,741,823 bytes. If you have 2 gigabytes, technically you have about 2 billion bytes. If you have 4 gigabytes, you have about 4 billion bytes. And it goes on like that. Now, the programs that are running on our computer and the data that is being processed by these running programs are stored in this RAM. The Central Processing Unit, or CPU, interacts with the random access memory. How does it do this? It copies the information it needs from the RAM and processes it, and then returns it back into the RAM. Let's take a look at what a CPU consists of. A CPU also consists of bytes, which are generally referred to as registers. Take note that in the RAM, these bytes are called cells, and in the CPU, they are called registers. There are different ways of keeping data in a RAM. Basically, 4 ways. You can either store it in 1 byte, 2 bytes, 4 bytes, or 8 bytes. Remember that 1 byte is equal to 8 bits, 2 bytes 16 bits, which is also referred to as a machine word. 4 bytes is equal to 32 bits, also known as double machine word. 8 bytes is equal to 64 bits or quadruple machine word. Data cannot be stored in 3 bytes, 5 bytes, 6 bytes, or 7 bytes. The computer only understands and allows 1 byte, 2 bytes, 4 bytes, 8 bytes of data to be stored. Now let's take a look at numeral systems. Numeral system is the basic way of writing a number. These are different methods of writing numbers. It is divided into 2. We have positional numeral system and non-positional numeral system. What this means is that in the positional numeral system, the value of a number depends on its position, while in the non-positional numeral system, the value of a number does not depend on its position. This is difficult to understand and remember, so it is not used now. It's not very popular. What we are concerned about is the base 2, base 10, and base 16. Let's take a look at these systems in more detail. The first numeral system we're going to look at is the decimal numeral system. It is also known as the Arabic numeral system or the Hindu Arabic numeral system. It is really not known who actually created it. But anyway, the decimal numeral system is a positional numeral system with a base of 10. By positional numeral system, what I mean is the value of a number depends on its position in the sequence. On this slide, we have 2886 written in the middle of the slide. Let's take a look at how the position of each of these numbers determines its value. Counting from right to left, we have ones, tens, hundreds, and thousands. If we multiply 6 by 1, we'll get 6. So let's just write a virtual 6 here. 8 times 10, 80. 8 times 100, 800. 2 times 1,000, 2,000. So by adding all these values up, we'll get 2,000 plus 800 plus 80 and plus 6, which is equal to 2,886. So you see the value of 8 here is in the hundreds, meaning 800. The value of 8 here is in the tens, meaning 80. Although it's the same number, the position determines its value. Recording numbers in the decimal numeral system, we use the following digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have 10, and so on and so forth. So these numbers are the numbers that we use to form any number we want. By putting them in the right position, we can allocate the right value to them. Let's take a look at a different numeral system and see the difference between the decimal numeral system and the other one. Let's look at the quinary numeral system. The quinary numeral system is also a positional numeral system, but this time with a base of 5. What this means is that we have 1, 2, 3, 4, and then 10. Basically, the Chinese people at that time, a very long time ago, they didn't have the numbers 5, 6, 7, 8, 9. So they only used 0, 1, 2, 3, 4, and then 10. In contrast, the decimal system or the Arabic system has 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So in those days, an Arabic guy is selling you 10 camels. He's really selling you 10 camels in the decimal sense. While if a Chinese guy tells you he's selling 10 dresses for you, you coming from an Arabic-oriented country, or should I say a decimal numeral system origin, you will not understand his 10. His 10 is your 5. Your 5 is his 10. So 10 camels in the decimal system or in base 10 system is not equal to 10 in base 5. Okay, this system uses like a one-hand method. In those days, the Chinese used one hand to count. So they have 1, 2, 3, 4 fingers, and then 10, and that's all. But the Arabic people used 2 hands to count. Just think of it that way. they used two hands. It wasn't very comfortable for them to use one hand, let's say. So they used two hands. That's why they have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. You can see 10 in the Chinese base or in base 5 is equal to 5 in the Arabic base or base 10. Alright, let's look at a different numeral system. This system is called the duodecimal numeral system. It is also a positional numeral system with a base of 12, meaning the position of a number determines its value. This system was used by the Russians some centuries ago. Although it's not being used now, I just want to show you that we have different numeral systems and somehow you can connect them. Okay, what are the numbers used in this system? How can we have 12 digits? They thought of creating a numeral system and they decided they'll have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9 they have A. After A they have B, and then 10. It's a long story. Just to cut down the story short, you see we have 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9 you get A, B, then 10, then 11, 12, and so on and so forth. So basically 10 base 12 is equal to 12 base 10. If we have 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, and then 10. In English, or in the decimal system, sorry, you have 9, 10, 11, and then 12. So in the duodecimal numeral system, there are 12. Our 12 is equal to the duodecimal numeral system's 10. Let's look at another numeral system, the binary numeral system. This is the numeral system that the computer uses. It has 0 and 1. These are the digits that are used. Now, comparing the decimal system and the binary system, I would want to use this table to give you an idea of how they are compared and the difference and so on. 0 in the decimal system represents 0 in the binary system. 1 in the decimal system represents 1 in the binary system. 2 in the decimal system is represented by 1 0 or 10 in the binary system. So basically they have 0, 1, 10, 11, 100, 101, 110, 111, and 1000. So comparing these two, you can see that 10 is 2, 11 is 3, 100 is 4 in the decimal, and so on and so forth. Now, the computer only uses zeros and ones, but it's not very comfortable to remember all these ones and zeros and so on and so forth. There are lots of combinations and it's not easy for the human brain to remember all this. It's easy for the computer and it works with it. Let's look at something else. Let's look at the hex numeral system. Now, I told you that the binary numeral system is not easy to remember. So programmers created a different numeral system. It makes it possible for them to just use one alphabet or one number to create or to represent a binary number. Look at this. Instead of using 0, 0, 0, 0, you just use 0. And in the hex system, they have 16, a base of 16. So you have 0, 1, 2, 3, 9, A, B, C, D, E, F. F is the maximum here. Now, why was this system created and how can we compare them? How can we convert from one system to the other? The hex system, as I told you, was created just to ease the workload on the programmers. They don't want to remember 1001 is 9, so they just write 9. They don't want to remember that 1010 is 10, so they just use A. 1011 is B. In the decimal, it's 11. So you can see that it's easier to just remember what E is instead of writing 1110. Instead of having 4 digits here, you have just 1 here, an alphabet E representing this. It ends with an F, but why? Ending with an F, we have a binary equivalent of 1111, which is half a byte or a tetrad, as I told you. Remember, we have the junior tetrad and the senior tetrad. Now, instead of writing 1111 to represent half a tetrad, we just write F. So it's possible for you to see somewhere 4A or 5F or something like that. What you should remember is 4 represents this, F represents this, but I'll show you this when we come to conversion and how to read numeral systems and hexadecimal numeral systems and how to use binary system. Recording numbers in the hexadecimal numeral system, the following digits are used: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, then 10. Now that we have an idea of the different numeral systems that exist, or at least some of them, let's look at the relationship between these numeral systems and how to convert from one system to the other. In this case, on this slide, we want to look at the relationship between the hexadecimal numeral system and the binary numeral system. Conversion is simple and very possible. There are different methods you can convert. So I'll show you one method now, and as we go on, I'll show you more methods. Now, here we have a number written in the hexadecimal format. Take note that 0x is a prefix used to show that this number is in the hexadecimal format, so that you don't confuse it with any other numeral system. Now, if you have a number in the hexadecimal format, what you do is you divide it into 2. Remember, I told you that a byte consists of 8 bits. These 8 bits are divided into 2. Counting from left to right, the first 4 bits, 0, 1, 2, 3, they can be referred to as the junior tetrad. And the last 4 digits can be referred to as the senior tetrad, or 4, 5, 6, 7, if you are thinking about their position in the sequence. So, now that we have written OX and have indicated that this is in the hexadecimal format, and we want to convert it into the binary format, let's look at this. We have a table here, and a hexadecimal row, decimal, and a binary one. So what we do is, since this number is in the hexadecimal format, we go to the hexadecimal row, and we look for A. We have found our A, and if you want to convert A into the decimal, you just go left and you have 10. But that's not what we want to do. If we go left again to the binary column, we have 1010. So we write 1010. If we want to convert C, we repeat the same procedure. We go C and then 0011, 0011. If you have just one number, then it means you have just one tetrad. The rest are going to be zeros. So, this is how a conversion from the hexadecimal to the binary system works. Let's look at the other way around. Now we can see that on this slide you have the relationship between binary and hex systems. And here we have a bunch of numbers. 1110, 1101. So we need to convert this number into the hexadecimal format. What do we do? First, you divide it into two again. You have two tetrads now, junior and senior. And remember, I told you if you want to represent a number in the hexadecimal format, you have to write the prefix 0x. So we just go ahead and write our prefix 0x and then look for these numbers in sequence. Since we have a full byte, we can start by looking for 1011 and write it here, and then we look for 0110 and write it here. If we have just half byte, we look for what is written here and we write it here. In this case, we have 1110. So 1110 in our table is E. We write E. Then again, we have 1101. We look for 1101. We have found it. And then we go to the hexadecimal row and we have D. So we write D. You can see how easy it is to represent this whole byte with 8 bits, 8 digits in just 2 letters or 2 alphabets. Sometimes they might not be 2 letters. You can have 2D, 4E. It depends on the value you want to convert. So let's look at a way we can manually convert. If you don't have a table, there is another way you can do it. You can mathematically convert from a decimal to a binary, for example. Okay? How do we do this? Conversion from a decimal number into a binary number is very easy. If you have, for instance, 41, which is a decimal number, a full number, and you want to convert this 41 base 10 into a binary equivalent, what you do is you consistently divide the number you have by 2 until you get a value that is less than 2. But let's follow this step by step and see how it works. Our given number is 41. 41 divided by 2. Well, we'll still get 1. So how many times can we fit in 2 in 41? We can fit it in 40 times. We write our 40. 41 minus 40. 1. We write 1. Then now we have another scenario. How many times can we fit in 2 into 20? 10 times. We write our 10. And 10 times 2, 20. 20 minus 20, 0. We don't have any remainder here, but we write 0. Now we think of the number of times we can fit 2 into 20. We have 10 times. Let's take a look at a different conversion. In this case, we want to convert a decimal number to a binary number. There are different methods of doing this. This method is just one of those methods. Now, the first thing you want to do is consistently divide the given number and the obtained integer results by 2 until the integer is less than 2. But what does this mean? This means that if our given number is 41, we divide 41 to 2, we'll get a remainder of 1, divide by 2, by 2, by 2, by 2. But let me explain it in a slightly different way. Look at it like this. Write the number of times 2 fits into the given number. Multiply the number of times 2 fits into the number by 2 and write the result under the number and result at its stage. Don't worry about this. let's just move on to this and I'll explain what I mean there. This means that I want to get a number in the binary format or in the base 2 format. So I have 2, base 2, I need 2. I divide my given number, in this case 41, by 2. So 2 goes into 41 20 times. Alright, we have a remainder of 1, but I'll show you what to do with it now. Next, I multiply 20 by 2 and I write my result under the given number. So 20 times 2 is 40. Now, 41, my initial number, minus 40. I get 1. Now I'm left with 20. So, how many times can 2 fit in 20? 2 can fit in 20 10 times. So I write 10 under 2. Then my next step is I multiply 10 by 2, which will give me a result of 20. I write 20 under this number. So 20 minus 20, 0. I write 0. I move on. How many times can 2 fit in 10? 5 times. I write 5. Then I multiply 5 by 2 and I get 10. 10 minus 10, 0. I write my remainder here. How many times can I fit in 2 into a 5? Well, I can fit it 2 times. So 2 times 2, I get 4. 5 minus 4, 1. I write my remainder under the result. Next, how many times can I fit in 2 into a 2? Just 1 time. 1 times 2 is 2. 2 minus 2, 0. Now, I cannot divide 1 into 2 without getting a fraction. So I stop here. Remember, until the integer is less than 2. And 1 is less than 2. So I just have 1 remainder here. The next step is you read the remainders from the last division sector upwards. This is my last division sector. This is where I stopped. So I read 1, 0, 1, 0, 0, 1. And I write it 1, 0, 1, 0, 0, 1. Now I have successfully converted a decimal number, 41, into a binary number. 41 base 10 is equal to 1, 0, 1, 0, 0, 1, 2. This 2 is base 2. So you see, it's very easy. Again, there are different methods of doing this. A lot of them. This is just one of them. How about converting from a binary number to a decimal number? This conversion is also very simple. There are just 2 steps involved. So let's take a look at the steps involved. The first step is you replace 1 in the number with 2, raised to the power of its positional notation. The second is you just add your obtained values. What does this mean? This means that if we have a number that is in the binary format, meaning it contains 1s and 0s, what we do is we change all the 1s for 2s and we raise them to the power of their positional notation. If you want, you can call this index or units. What I just want you to understand is counting starts from right to left. So 0, 1, 2, 3, 4, 5. Now, writing this number below here and changing all the 1s for 2s, we have 1, 2, 1, 2, 1, 2. In this method of conversion, zeros are not to be converted or are not to be replaced by anything. You just omit them. So the first one here, which we replaced with a 2, is raised to the power of 0. So we write 0. The second one here, which was also replaced with a 2, is raised to the power of 3. We omitted 0, 0, 0, 0. So it's in the third position. The third one here, which was also replaced by 2, is raised to the power of 5. So now, let's calculate our values and add them up. 2 raised to the power of 5, get 32. 2 raised to the power of 3, we get 8. 2 raised to the power of 0, we get 1. 32 plus 8 plus 1 is equal to 41. So 100101 in base 2 is equal to 41 in base 10. You can see how easy it is. But then again, there are even easier methods. I'll also show you, but this is one of them. The next conversion type on our list is converting a decimal number to a hexadecimal number. Now, remember that a hexadecimal number is a number that is in base 16. So, what we do is we consistently divide our given number by 16 until we get a result which is less than 16. In this example, we have 1225 divided by 16. We'll get 76 divided by 16, and we get 4, and there we stop, because 4 is less than 16. So, let me tell you another way you can think of this. Write the number of times 16 fits into the given number, multiply the number of times 16 fits into the number by 16, and write the result under the number and each result at each stage. Basically the same thing. 1225, and we have 16. So how many 16s can we fit into 1225? We can have 76 16s. And then we write 76 times 16. We'll get 1024. And subtract 1024 from our initial number. So 1225 minus 1024. We'll get a remainder of 9. So we write our 9. Next, we see how many 16s we can fit into our result, 76. So we can fit 4 16s into a 76. So we write 4 here. 4 times 16, we get 64. 76 minus 64, we get 12 in base 10. But then again, in the hexadecimal system, 12 doesn't exist like 1, 2. So what exists is C. C is like what we can use to represent 12 in the decimal system. So here I'm calculating in the decimal system, I have 12, and 12 base 10 is equal to C base 16. So I'm not going to count this 12, I'm going to count C, because I want my result to be in the hexadecimal numeral. Let's read it from the bottom. 4 C 9. So 1225 base 10 is equal to 4 C 9 base 16. And that's it. Very easy to convert. Okay, let's try converting a hexadecimal number to a decimal number. There are 2 steps involved too. Multiply the number by 16 in the power of its respective position. Second step, add the values. Here we have an example, 5A. 5A is written in the hexadecimal system. Now, if we want to convert 5A into a decimal system, we need to multiply 5A by 16 and then in the power of its respective position. Let's take a look at what this means. We write 5A. And remember that counting from right to left, we have 0 and 1. That's the indexing or base. So 5 times 16, and 5 is to be raised to the power of 1. So 5 times 16 raised to power 1 plus A. Remember that you cannot put A in the decimal system, but A represents 10 in our table. A in the hexadecimal system represents 10 in the decimal system. Remember, in the hexadecimal 16-base format, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, then A. So that A is 10 in the decimal system. Now, we write 10 instead of A and then multiply it by 16 raised to the power of 0. So, here we have 5 times 16 raised to power 1 plus 10 times 16 raised to power 0. 5 times 16 is 80 plus 10 is equal to 90. So 5A base 16 is equal to 90 base 10. Don't get confused with this 10. I told you that A in the 16 base is 10 in the decimal base or base 10 system. Now that we have seen some conversion methods from one numeral system to another, let me show you an even easier approach. If you're not friends with pens and papers and you don't like calculation, there is a good friend I recommend, the calculator. A programmer's calculator in specific can help you convert from one system to another without any effort. Let's look at how this is done. As an example, we used 41 in our previous slide in the decimal format and we converted it into a binary format. And you have seen the steps. We had to divide 41 by 2 by 2 by 2 until we got a number which was less than 2. In this case, you don't have to divide anything by 2 by 2 by 2 by 2. What you just need to do is to input 41 in the decimal system and you change it into the binary system. You just click this if you're using a computer or change it if you're using a calculator. So, once you do that, it will change to a value in the binary format and vice versa. If you change this back into decimal, it will display 41. If you change it into the hexadecimal format, it will give you your result. Very easy. I personally recommend a calculator as it makes the job easy and it also eradicates or gives you an upper hand. You will not make a mistake using the calculator. Let's put the mathematics aside for a minute. Let's look at something called a variable. A variable is a memory area that keeps a value that can be changed. What does this mean? This means that you can create a variable, assign a value to it, and then later as your work goes on, you can come back and change this value of a specific variable, and then it will automatically change in all your code where you have that variable. You do not need to individually go through all the code and change the value of that variable. You can change it once and that's done. Now, I told you that in a random access memory, you have a lot of bytes. depending on the number of gigabytes or megabytes you have, a variable takes one random address and saves the information you assign there, the value you assign. In this case, we have 2. A byte-typed variable is a type of variable that can keep up to 8 bits. Here we have assigned 2, and you remember that in the binary system, 1, 0 equals 2 in the decimal system. So you can use your decimal system here, and the computer will automatically convert it into the binary system and save it for you. Now that we have a little idea of what a variable is, let's take a look at how we can create a variable. Creating a variable is easy, but you need to specify what you want. You need to specify the type of variable you want. In this case, we want to create a byte-typed variable, which can hold up to 8 bits. And you need to name your variable. This is called the identifier. And then you need to assign a value to your variable. You assign a value to your variable using the assignment sign. So, now we have a variable created. This is how you can read this variable. You have created a byte-typed variable named A, and you have assigned a value of 2 to your variable. So, whenever you write byte A in your code, it will automatically have a value of 2. If you change the value of your variable, it will change in all the places where you have byte A. So you have created a variable and you have initialized it. You can initialize a variable by assigning a value to it. Now, if you remember earlier on, I told you that a byte can keep up to 8 bits. The maximum data you can save in a byte is 8 bits. And the maximum value you can assign to a byte is 255. So what happens if you want to assign a value of 256? It's just +1. It's not a big deal. Well, a byte cannot handle it. In this case, what we have to do is we have to add an additional byte. So here we have 1, 2, 3, 4, 5, 6, 7, 8. We have 1 byte, which can hold a maximum value of 255, but we need 256. So we take another byte and we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 2 bytes here. Short is a type of variable that can keep up to 16 bits. Byte can keep up to 8 bits. Short can keep data up to 16 bits. So, if you want to assign a value of 256, you must have 2 bytes so that you can assign a value of 256. On this slide, we have some ways of keeping data in a RAM. Here we have 4 different ways. We can save it in a byte, in which case we have a maximum of 8 bits, but a byte can be just a byte unsigned, or it can be a signed byte. This S means sign. It means if you want to create a byte that has a negative value, you have to create an S-typed byte. If it is of a positive value, you can create just a byte. Bool, on the other hand, is not about bytes. Bool is a keyword and it's short form of Boolean. It is used to store the Boolean values, true or false. Boolean is the surname of some mathematician that created this in the past, a long time ago. So if you need to create a true-false scenario, you can use the Boolean or short bool. So the short name for Boolean is bool. Now, if we have 2 bytes, which just on the previous slide I told you can hold up to 16 bits, and this is also called a machine word. You remember I showed you what a short is. But again, we have U-short. U-short means unsigned short. In this case, short can be signed. It can have a positive value or a negative value. But unsigned short can only have a positive value. Okay, let's look at char. Char is used to declare an instance of the system.char structure that the .NET framework uses to represent a Unicode character. Now, in a short way, I can tell you that char is for keeping characters, Unicode characters like A, B, C, and so on and so forth. But I'll explain this in more detail in our next video. Okay, we also have 4 bytes, which is equal to 32 bits. This is also referred to as double machine word. If in 2 bytes we can keep a maximum of 16 bits, then in 4 bytes we can keep a maximum of 32 bits. Logical. Okay, here we have integer. Int is like the short of integer, which means like a whole number. Here you can keep a maximum of 32 bits in this, and it can be a negative sign or it can have a positive sign. Then we have unsigned integer, which is also a whole number, but unsigned integer cannot have a negative value. It can only have a positive value. Fine. Next is float. This is what we can use, or the keyword we can use to create a variable if we want to save a fractional number. Not an integer number, which is a whole number. We want to save a fractional number. It can be 2.345, 3.213, or something like that. So if you want to save a fractional number, you want to create a variable and assign a value which is in a fractional number, then you need to create a float. This also I will elaborate more in the future. Now the next one is 8 bytes, which has a maximum capacity of 64 bits. It is also called the quadruple machine word. Now here we have long, ulong, and double. This long is used to create a variable that has up to 64 bits capacity. Long can be negative or positive, but unsigned long, U stands for unsigned. Unsigned long can only have a positive number. Then we have double. Double is similar to float, but double has a longer tail. By tail, I mean the number of digits you can have after the period sign or dot in a fractional number. So in float, you have a restriction. You can only have a number of digits that you can save after the period sign in a fractional number, but in double, you have more precision. You have a lot of numbers you can keep after the decimal sign or the period sign in a fractional number. Again, I will show you more examples. I'll give you more information when we come to our practical part. Okay, very good. Now we have taken a look at data types. We know about predefined data types, simple data types, non-numeric, numerical, integer, real, and so on and so forth. But what do these things look like in practical? Yes, this is a very beautiful diagram with a lot of things. I know we have not looked at object and dynamic. We will look at that in our next course. Don't worry, you don't need them now. One thing at a time, step by step, and we'll get there. But you know what bool is, char is, s byte, byte, I have explained. But how do they look like, or what do they do in a program? If you have a project, how can you use them? This is exactly what I want to show you now. So let's move on to some exercises and examples, and I will show you what I mean by bool, byte, s byte, short, u short, what you can do with them and what you can't. So for us to open some examples and take a look at them, we have to open Visual Studio, Microsoft Visual Studio. That's exactly what I'll do now. So if I open my Microsoft Visual Studio, you'll see that with this course we'll attach some exercises for you, which each lesson has its own exercise and each course has a set of exercises. So what you do is you open this. Yes, we have properties, references, program.cs. This is what you are interested in. So we go to 001, type basics, and then we have program CS. We click on this and we have something written on our screen. So let's take a look at all these things and we'll see what we mean. Remember, a variable is a memory area that keeps a value that can be changed. Now let me show you what a variable is just in the real. We have namespace here, class. Don't worry about this, I'll explain them later. For now, you don't need them to understand what I am doing. Static void main, just understand that for now you don't need this now. Void is somewhere near the 6th or 7th class, and we'll have, when we start studying methods, I'll explain void and things like that. The main thing I want you to understand is the word main here. So main, what is main? Main is like the entry point. It's where the computer first goes to when you initiate a program. When you start a program, the computer first goes to main. It's the entry point. And from there, it might be referred to or returned to or sent to another part of your program. But first, it goes to main. And from there, it can be sent to other places, maybe to methods, maybe to conditionals or something else. But for now, just take it that main is the entry point. It's where the computer first goes to. So let's see what a variable is here in practice. A variable is a memory area that keeps a value that can be changed. What does it mean? Keeps a value. What does can be changed mean? Let's take a look at this step by step. Now here on line 13, we created a byte typed variable. We named it age. So here is the type of variable you want. You can have byte here, you can have short here, you can have long here, you can have int here. It depends on the value you want to assign to this type. So to this variable, sorry. So here is the type, represents an 8-bit unsigned integer. Remember, we have signed byte and unsigned. So but we don't say unsigned, we just say byte. So it's 8-bit unsigned, just byte. And here we have the variable. Remember, I told you that to create a variable you need 3 things. Yes? So let's go back to our slide and take a look at these 3 things you need when you are creating a variable. Here we go. So when creating a variable, you must specify the variable name or the identifier. Type of variable. Variable name, this is it, identifier. In this case, we have a variable name. Type of variable, here we have byte. And then The initial value, well, optional. Here we have a value. You have to set a value to it. This equal to sign is not equal to in programming. This is an assignment sign. It's like variable name A, type of byte, and then we assign 2 to A. So in your program, anywhere the computer sees A, it will assign 2 to it. This is done to make the job of a programmer easy. You know, you don't have to go through all your code and changing A is equal to 5, A is equal to 5, A is equal. You can just change it in your variable and it will change it automatically for you. So let's go back to our programming and see what happens. Open Visual Studio again, and here we have created a variable, a byte typed variable, which we assigned a value of 25 to it. And remember, I told you this semicolon is very important. If you don't put the semicolon, you will have an error here. You see this red line here, it means we have an error. So this program will not run until you put a semicolon. It shows the computer that this line is finished. This is finished. So now we have created a variable. Okay, we have created a variable, but then I said it's a memory area that keeps a value. So let me show you what a memory area that keeps a value is. We go back to our slide, this slide, and then here we have a variable is a memory area that keeps a value that can be changed. Here, just as in our example, we have created a byte typed variable. We named it A and assigned a value of 2 to it. So what are we telling the computer? Remember, a byte is 8 bits, okay? And the maximum value of a byte can be from 0 to 255. So here 2 is less than 255, so we can assign 2 to a byte typed variable. Now the computer doesn't understand this. What it understands is this. Remember, 00000010. In the binary system, which this B stands for, this just means that it's in the binary system, okay? This is 2. So this is what it looks like. The computer now assigns this value that we have and it puts it somewhere in the memory, in some, I don't know, it can be here, it can be here, it can be here, we don't know. In this case, we just put it here just for easy access. So you see we have here 0000, we have allocated 2, the value of 2 to this byte. We don't choose the byte, the computer chooses the byte, and we don't care where it is. All we want to know is when we call it, it comes to us. And we say, we want the value of A, the computer will go and look for it and bring it to us. Okay? Fine. So, now you have seen this. Let's go to another slide and see what happens. Okay, here we have short A, which is 256. I told you that 255 is the maximum that a byte can hold. So what if you want to have a value that is more than 255? What you do is simple. That means a byte can no more hold your value, so you look for another one, short. A short can hold 256 easily. So you create a short typed variable named A and you assign a value of 256 to it. In which case you would need 2 bytes. Remember, for byte we have 1 byte. For short we have 2 bytes. Yes? Okay, let me show you. Let me just remind you. Here we have it. A byte, we have 1 byte. For short, U short char, we have 2 bytes. For int, U int float, we have 4 bytes. For long, U long double, we have 8 bytes. Okay, so if you want to allocate something, not a very big number, you can use byte. If it's a little bit bigger, like 1,000 or 500 or something, you can use this. If you need numbers in millions, then you can use this. And if you need more space, and you can use 8 bytes. So remember again, the computer does not have 3 bytes, 5 bytes, 7 bytes. It just has 1 byte, 2 bytes, 4 bytes, and 8 bytes. Okay, fine. Let's go back to our Visual Studio. Now we're back. So I guess you understand that here we created a byte typed variable, we named it age, and we assigned a value of 25 to it. So what next? We want it to be displayed. We want our 25 to show on the screen. So what do? You write console write line. Console is like calling your name. Like if you say Rashid, stand up, and I stand up. So you are telling the console to write the line. Do you remember what the console is? Console is your keyboard and your screen. That's correct. Keyboard and screen. So you are telling the console to write it, to display it on the screen where you want. So console write line, age in brackets, parentheses as they are called. So what will happen if we run this program? We're not going to see age written. We're just going to see the value of age. It is not correct to say we want to display a variable on the screen. No, we can't display a variable. But what we can do is we can display the value of that variable. So if I run this program, what will happen is we'll see 25 on the screen. Okay, let's try it. Remember, start is run. Okay, run. Let's run it. All right, here it is. Let me just resize it a little. So you see 25. Simple. Very good. But let's see. What if we change the value of 25? What if we put 35, for example? What will happen? The same thing. It will just display the value that we have assigned to it. Let's run it and see. Now we should see 35. Okay. It's out again. Anyway, you see 35. So you can change the value and display the value that you want. Let's just put it back to 25. Control S. Remember, when you change a value and you want to go back, you have to save it, yeah? So you press Control S. Okay. Now, very good. Let's see what's next on our exercise. What we do is we just put this back and let's look for alias and program CS. Well, every time you open a new program, you see it's like, you have first program that we had here. Remember variables, about variables using the system. And then here we have alias, that's the name. Here we have type basics. So let's close this type basics. Since you understand everything that is here, I'll just close it here. And then we'll go to our second example, alias. What does it mean? Alias simply means like a nickname, like, well, not the full name, not the real name, like a nickname. So again, forget about 1, 2, and 3. Okay, remember that main is your entry point and we'll start from here. All this I'll explain as we go on. So here we have created a variable, a byte typed variable named A, and we assign a value of 2 to it. You remember, we just did this now. And it's an alias byte typed variable. Why is it an alias type variable? Because you can see here we have, it's even in another color, yeah? We have the same thing. We created a byte typed variable named B and assigned a value of 2 to it. But the computer sees these two as two different expressions, two different variables. Why? Because here you can see we have a small letter b and here we have a capital letter B. So that's basically the difference. This is the full name of the byte or the variable that we created, and this is like an alias name. It's like a nickname, yeah, of the type of variable that we want to create. So Here we assigned 2, here we assigned 2, the same thing. Then we go to the console and we write console write line A in brackets, console write line B, the same thing. So what do you think will happen if I run this program? Well, if I run this program, what we should see is 2, 2. It's not gonna look at them as the same, variables. No, there are 2 different variables to the computer. Let's try this and see. Run, and there we have it, 2, 2. Meaning what? We have variable A is 2, variable B is 2. But let me prove that to you, because you might say that, well, it's just a trick or something like that. They are not the same. They are the same. Let me change this. Let's try this. If we assign 7 to this, okay, I want to prove that there are absolutely 2 different variables here, although they have the same type, but this is an alias type and this is the full name. The computer sees them as 2 different variables. So let's run it again. Start. Here we go. You see, variable A 2, 2, variable B, which of course is also a byte type. This one is also a byte type, but this is an alias and this is a full name. So we have changed it to 7. You see? And if you change the value of variable A to 5, for example, you will have 5, 7 now. Yeah? We have 5 and 7. 5, 7. So you see, you can create also using byte and okay, I've just put that back into the normal, and I'll save again. Remember, save, Control S, save. So what I was trying to say is, although we have byte and byte, simply by capitalizing the second byte, we have the full name here, and here we have the alias name. So you understand that an alias name and a full name are different. Yeah, we have it here on line 11. We created an alias byte typed variable named A and assigned a value of 2 to it. Okay, let's just make that smaller. Then if you want to just zoom in and zoom out, you press Control and you just rotate the roller on your mouse and just roll it down or up. So then on line 15 we created a full name byte type. Here we have alias byte type, here we have full name byte type. Okay, so I guess you understand it's very easy. Full name, alias name. That's just what alias means here. Okay, well, let's see something else. Let's go back to our presentation and let me show you something. Here we have, remember we looked at bool, char, byte, s byte, short, u short, int, u int, long, u long, decimal float. Let's see what they are. Let's just go back to Visual Studio and we'll see. Let's just collapse this and open this. We have basic types here, lesson 3, basic types, or should I say example 3, sorry. So we open this here, basic types. Again, keep this out, main, and we enter from here. Okay, here we have our curled braces, so we start from here. Let's see integer types. Integer types. Integer types are, well, I told you there are types that are whole number types, not fractions, just whole numbers. So they keep a whole number. So let's see what we mean. Remember, 8 bits is equal to 1 byte. Double equal to sign in the computer, it means equal to. And a single equal sign will mean assignment sign. Okay, assignment sign and equal to sign. So this is equal to sign. We have 8 bits is equal to 1 byte. Integer without a sign range from 0 to 255. Well, this is a byte. Yes, a byte. So this is the alias name with a small letter, and this is the full name with a capital letter. Again, here we have 0 and 225. So this is the minimum and this is the maximum that a byte can hold. So, but then again we have S byte. We looked at S byte. Do you remember? And I told you S byte, it means a signed byte. It has a sign. So what does this sign mean? It means positive or negative. Positive or negative. It's not very correct to say that this is a positive number. No, it's just a number, okay? This is just a number. But here we have, it can be positive, it can be negative. So for S byte, the minimum here is minus 128, minus 128. And the maximum here is plus 127. So again, S byte alias S byte full name. That's 1 byte, okay? Then we have 2 bytes. 2 bytes is 16 bits, yeah? 2 bytes, remember I told you this is equal to 2 bytes. 16 bits is equal to 2 bytes. Okay, good. Integer without a sign. So what we mean here is U short. Here we have unsigned short. Unsigned without a sign. Here we have unsigned integer 16. What this means is 16 bits. Okay, look at it. Represent a 16-bit unsigned integer. So here we have unsigned for integer is 16-bit, and for U short is also 16 bits. Fine. So here we created a variable, a U short variable type, and assign a value of 0 to it. Here we created an unsigned integer typed variable named f and assigned a value of 65,535. That is the maximum that a short or uint16, U short or uint16 can hold. Minimum, maximum, okay? So now this is the unsigned without a sign. Let's go to the signed ones. If you just see a simple short or just int16, it means that it is a signed value. Here you see represents a 16-bit signed integer. 16-bit signed integer. So here we created a short typed variable named g and assign a value of minus 32,768 to it. So again, a signed value can have a negative or a positive value, whilst unsigned is just a number, okay? Good. Now remember again, as we're talking, you have, for example, here 1 byte, 2 bytes, the computer does not understand 3 bytes, so 4 bytes, yeah? And from 4 bytes, we have 8 bytes. Okay, fine. Before we go to 8 bytes, let's just look at the unsigned integer. Now we have unsigned integer I, and you have 0 U here. U, this suffix U here means it's unsigned, unsigned. So in the value, you can put U here, and it means it's unsigned. uint32. Now 32 is the full name. It's 32-bit unsigned integer. Here we have 16-bit alias name, and here we have 32-bit full name for it, okay? Full integer. 32-bit signed integer, and we assign a value of, oh, I don't want to read this. Anyway, so we have plus this. You can see a lot of numbers here. All right, let's go to 64 bits and 8 bytes, which is the maximum here. So we have integer without a sign, range from 0 to this, okay? So we have ulong, we create a variable, a ulong typed variable named m, and we assign a value of 0 to it. Well, this is the minimum here. And then you have ul. That's what I want you to see here. You have ul. Ul means unsigned long. It's just a suffix used to show that This value is in the unsigned long type. Fine. Then we have uint64. Assign a value of this to it. Okay. Remember, you cannot have negative here, so just leave it like this. It's unsigned, no sign. But if we want to create a signed long type, we can create it. There is long and int64. Now, int64 is the signed version. You can have plus or minus, and here we can also have plus or minus. Yeah. In this case, we have L long, okay? So here we go. This is the difference between unsigned and assigned type of variable, okay? These are the basic types that we have here, signed and unsigned. Let's collapse this and, okay, and go to real types. Let me show you again. Remember here we had real types, yeah? So we have real, decimal, float, and double. And I told you that the difference between them is the precision. Yeah, it means how many digits they can hold after the decimal point. All right, real means like fractional number. Integer means whole number. So we have an idea of all this, and you've seen that none of the examples I gave you were in fraction. But here, this is what we use if we want to show a fractional number. So let's go back to our presentation again. Sorry, not presentation, to our Visual Studio and open real types. Real types. Okay, fractional types. Real types are intended to represent fractional numbers. Okay? 32 bits is equal to 4 bytes. All right. Real with a sign. It means it has a sign, positive or negative. Okay? So this is float, single. Float is the alias name, single is the full name. So we have float. We create a float typed variable named G and assign a value of minus 0. You see it here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have F. What this F means is that it's in the float type. It's the float type, okay? So this F means float type. Now, if you count this, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, 9 here. Here we have single, which is the full name. We created a variable, single type variable named R, and we assign a value of plus. So you see here they have a sign, and the other thing I want you to notice is 1.1, 2, 3, 4, 5, 6, 7, and F. Okay? Now, this is it. If we have this FF, it's not that we must put it there. But what's the reason? Why do we put this reason? It's because the compiler interprets this number as a double on default. So if you don't put this F, the compiler will think of this number or will accept this number as a double. And we'll see what a double is right now, okay? Let's go to double. 64 bits, 8 bytes. Here we have double, okay? Now, real with a sign, range from minus to plus whatever. Anyway, here we have double. We created a variable, a double typed variable, and you have this 0 point, and then you have D at the end. It's not necessary to put this D because the computer will just, on default accept it as D. But any case, I just put it here just, to make it easier for you to understand. Float, single, and double. Take note, single, we don't write S, we write F, a capital F. So, this is a double and float. The difference is in their number of digits they can hold after the decimal point. Let's move on to another type of variable. Remember, we have integer types, we have real types. Now we're going to move into decimal type. Now, the decimal type is also used for storing decimal numbers, just like real types, but with a higher precision. Remember, in real types we had float and double. The difference between them is that double is more precise. Well, now decimal type is even more precise than double. Let's see what we're going to have here. Alright, this type is used also to store fractional. As I said, it can be signed. You see here we have minus and here we have plus, and we have the alias here, decimal, with the D written in lowercase, and we have the full name here where you have decimal with the D starting with a capital letter. You can see a difference even in the color in which it is written. So now you might be wondering, well, we just have like 1 2 3 4 5 here. Well, you can have a lot. You can see the range here. You have the range. So basically this is used in banking, you know, where high precision is required. You might be wondering what this M is here too. Now this lowercase m and this capital M tells the computer that the number you just put in is in the decimal type. So there is no need for putting, let's say, D or F. If you put F, remember it's float type. If you put D, double type. If you don't put anything, it's double. So you have to specify that this is decimal. That's why you write an M here, okay? All right, let's move to another type, which is the Boolean type. Now, the Boolean type is used for storing things like true, false, and that's it, okay? George Boolean, I think some guy that created it. You can see bool is like the alias, and then Boolean is the full name. So we have true, false. You can keep a logical value of true or false using the Boolean type, okay? So the Boolean type is used for storing logical values like true and false. All right, let's look at the character type. The character type is used for storing one character, like A, capital A, or B, capital B, or lowercase b. The short form for it is char. It takes 2 bytes and it's 16 bits. The characters are in Unicode format, so always have them in Unicode, Microsoft Unicode format. All right, if you see this, you'll find out that we have not only a semicolon, but we also have, you know, a quotation mark here. If you remove it, you have an error. So please try to put it. It's not double quotation, it's single quotation. So just if you want to store characters like this, you have to put single quotation, and then don't forget also to put your semicolon. Now this is used for storing one characters. But what if you want to store more characters? What if you want to store a name? What if you want to store a longer word? This is the one that you're supposed to use. You're supposed to use the string type. Now with the string type, you can save a lot of things. You can see here, string, my first string, and we assign hello to it. So we create a variable named my first string of a string type, and then we assign a value of hello to it. Now this is what we want to assign. You can assign anything. You can write your name here or something. It is also in Unicode format, but here you see hello. But if it is char, like class char, or you have like you can only put one character. So this is the string type in short, but we're going to elaborate. Don't worry. As we move on, you'll learn more and more. If we go back to our Solution Explorer, we'll open another project and see some examples. Yeah, let's open another project. Fine, here we have int. That's good. Now any project you open will be saved up here. If you want to close it, you can just close it like this, close, or you can right click on the one you want and then close all but this one, okay? So but now let's just close this one since we just have one. Save changes. Fine. So here we have another thing. We have, if you remember how to read this, we created a variable named a here, and it is of an int type. So it means we can save whole numbers here. Yeah, it's not uint, so we have to save just numbers without a sign. How does this work? Here we also create a variable named b and assign a value of 2 to it. Okay. At line 11, error, use of uninitialized local variable is prohibited. What does this mean? What does initialized mean? Initialized in this case means that you have to assign a value to it. Here, if I assign a value and let's say I put a is equal to 4, everything will be okay now. Okay, now we can run this, it's fine. If you say console read line, let's try it and see. F5. All right, here we have 2, okay, because we say console read line B. Let's remove this quotation marks and console read line A. Now we should see 4 and 2. 5. You see it here, 4 and 2. So what was the mistake? The mistake was we didn't assign a value to this, meaning it wasn't initialized. So you have to initialize something. You have to write something, yes? You have to initialize each line. So here we have console write line A, console write line B. It's not gonna write anything for A now. Let's see. There were build errors. Would you like to continue and run the last successful build? No, I know my mistake and I'll correct myself. So this is it. This is the meaning of initializing a variable. Yes, you can create a variable. You can even name it and choose your type. But if you don't assign a value to it, it means you did not initialize it. Okay? Fine. This is the meaning of initializing. Let's move to the next one and see what we have here. Remember again, let's just do it like this. Close all but this. Now you understand what I'm doing. Nope. So here we have the difference between float, double, and decimal types. Imagine we have a variable. We create a variable, float typed variable, and we name it variable 1. We also create a double typed variable and name it 2. Our third variable is named variable 3 and it's of a decimal type. And we have the same numbers here. We have just the same thing. And at the end here we have F for float, D for decimal, and D for double, and M for decimal. Now console write line variable 1, console write line variable 2, console write line variable 3. This is what will make your variable show on the screen. Okay, now let's run it and see the difference between these three. If you compare this, you'll see that we have 0.123456 Here we have 0.1234567891091011 10 sorry, and 0 1 2 3 4. All right, anyway, the idea here is for float we can only save 1 2 3 4 5 6 7 digits after the decimal point. For double we can save 9 10 11 12 13 14 15. So we can save about 14 digits after the decimal point. But for decimal we can save a lot. You see, decimal holds a lot of digits after this, so it's more precise. Okay, let's quickly go to the next slide and I'll show you something about char or character. Remember I told you that char is used to save characters. Let me show you another way you can save it in different formats. Okay, here we have created three variables: variable A, variable B, and variable C. All of them are of char type, and then we assigned a value of variable A, which is of char type. We assigned a value of A to it, capital A, and remember these quotation marks, they are very important. B is also a variable that we created, a char typed variable, and assigned a value of x0041 to it. C is also a char typed variable which was assigned a value of u0041 to it. Now this is nothing special, don't get confused. X means this value is in the hex format, U means this value is in the Unicode format. Basically they are all the same thing. if I run this program, you'll find out that 3 A's will be displayed, 3 capital A's, because 041 and 041 in U and X formats, these is just the code, or these are just the codes for the hexadecimal and the Unicode format for A. Okay, so let's run it and I'll see what will happen. It's out, bring it in. So we have 3 capital A's, meaning that the computer sees this as A, sees this as A, and sees this also as A. These are just codes for the capital A. Let's stop running this program and let me show you something. What if I change this to 2? What will happen? Let's change this to 2, meaning 42, and run the program. Now you can see that A has been changed. We have changed it to capital B. So the code for capital B is 42. What about if we change it to 61, for example? Let's change it to 61, okay? And run the program, F5. Do you see this? 61 is just a code for lowercase a, and that's it. So these are just codes that are used for the hex format, Unicode format, to type in or to print characters to your screen. Let's change this back to 41. Okay? Always put back what you have changed, or you can create another copy of this and then play with it just to see how things will go for you. So this is how char can be used, and different formats can be used to write the same thing. So thank you very much for your time and attention. I hope you have enjoyed this lesson, and I hope you have learned something very interesting and you will use it in the wisest way possible. Once again, I'm Rashid Hamid, working for Cyber Bionic Systematics. See you next time.